It is videoing. Alright, so your classic potential divider looks like this. It's really helpful if you're going to start doing equations to use subscripts. For the subscripts to mean anything, you have to actually label your resistors. You have R1, R2, label your voltages, V1, V2. This thing is going to be V tot, which obviously equals V1 plus V2. You will then have something here called I tot. Now in this circuit, there's only one current, so I1 and I2 is equal to I tot, and that's fine. Now, hopefully this is relatively simple, and we have some basic equations which we'll talk to you about, like R1 over R2 equals V1 over V2. Or you could write it in terms of tot and the rest of it. What you often get is something which is a bit more subtle. So an example might be they draw something like this. Okay, how is something like that possibly going to be a potential divider? Not quite. What could this be hiding? An internal resistance. So you could have an internal resistance which they didn't draw on, but you do draw on. Now this is the same circuit as that. Yeah, because this is my R1, and then this thing has just been brought round the wire. Yeah, and that's R2. Yeah, a little bit confusing. This is V1, this is V2, and V2 is what we call lost volts now. And then this is V tot. Okay? Now, terminal voltage, confusingly, would be that. So we would have to be careful there. So that's one way in which it can get more complicated or a bit more tricky. The other really common way is that you, instead of just having a single resistor as R1, you actually have a parallel combination. This is still a potential divider, but so long as we call all of this R1 and we call this one R2, and we still have V1 as before, and we still have V2 as before, and V tot as before. Now everything applies the same as it did with the original one, but within R1 we've now got, I don't know whether we want to call this RA and RB. Within R1 we've got this equation. Can't do it that way around. Oh, that's really helpful. R1 equals 1 over 1 over RA plus 1 over RB. Yeah, so that's the only real difference there. But this throws people a lot. And when they ask you to do explanation questions, the explanation questions are almost always on something like this or something like this. If it's something like this, they want you to talk about how the current is going to increase or decrease, and that's going to affect V2, which they're going to want you to call lost volts. So for example, if I decrease the resistance on this, total circuit resistance goes down, current goes up, lost volts increases, and that might affect something like dissipation or whatever. Right, I'm going to talk about explaining with this guy here. Often it'll be this structure, but one of these guys will be replaced with what kind of component? A what? Yeah, a thermistor or? No. Kind of a variable resistor, yeah. Other than a thermistor, what else is there that could be used in a light sensing circuit? Yeah, we could have an LDR. So it's going to have this shape, and then either this for thermistor, or this for LDR. Yeah. Okay. Then they're going to give you some information like temperature increases or light intensity increases, and you're going to have to explain stuff. Now, the most common mistake here, literally everyone in the class made, is they're familiar with this equation, and they'd see, ooh, resistance has gone down. Therefore, voltage must have gone down. Yeah? What have they assumed? In order to take that and say that V is proportional to R, what must be true? What's the difference between that equation and that equation? Yeah, you've had to assume that I is constant. Interestingly, some people, even in the same question, have done this. In the same equation, they then said, oh, well, R's gone down, so I must have gone up. Yeah? We can't do this kind of stuff. The other mistake was to interchange which R you're talking about and which I you're talking about. So, for example, the resistance of this has gone down, therefore the current of this has gone up. It's like, hold your horses. Yeah, we've got separate equations for each one, but in order for us, we can always use this equation, but to assume that like any of these is constant, we have to actually know that. So a really good thing to do in this is to really think, what are my constants, and therefore, what relationships can I draw? So tell me, in this, well, first thing I'm going to do is, with this kind of question, is label everything. Yeah. So I'm going to label this whole thing here. I'm going to call it R parallel. I could have called it R1, but it gets confusing if the question starts labeling that thing R1. Yeah, I'm going to call this one RC. Yeah. And then this thing here I'm going to call V tot. This thing here I'm going to call I tot. What other I's have I got here? Yes, I've got I LDR, and I've got I'm going to call that B. Yeah? So now I'm aware that there's some stuff. I'm going to call this thing VC, and I'm going to call this thing V parallel. Once I've labelled that, the question becomes so much easier. You're much more likely to start getting things right. Before we dive into it, to check some understanding, I want you to tell me which of these physical quantities are constant. And one of the physical quantities that's constant I haven't even labelled, so I want you to find the missing label, but also tell me which things are constant. I'll give you a little moment to work that out. Yeah, so think about the components and what the component is built to do. This is a cell, and it's built to have a potential difference across it, a fixed one. So, for example, 6 volts. So there will always be 6 volts across this. I mean, that's an idealization, but that's what it's built to do. That's what we assume. Currents are always changing because they depend on voltage and resistance. The other thing that's going to be fixed is these other components that are built specifically to have a value. So resistors are built with a specific resistance. We haven't labelled this on here. I'm going to label it RB. So RB will be constant, RC will be constant, V tot will be constant, and that will allow us to use relationships like this in specific situations. So the next thing I want you to tell me is what relationships like this can we actually pull out from this circuit? So which relationships can we pull out based on the fact that, or we could do it one at a time. There's going to be one relationship based on V top being constant, one relationship based on RB being constant, and one relationship based on RC being constant. So first of all, V tot is equal to I tot times what? R tot. What's R tot? It's going to be that one plus that one. Yeah? Okay, so if V tot is equal to that, and this is constant, what relationship can we draw out? We can draw out this kind of one. So we can say I tot is proportional to 1 over R tot. Happy? So that's the key relationship. We might note that down. Let's pick one of the other components. Let's say RC. Let's write RV equals IR for RC. So VC equals, in this case, IC is I top times by RC. Yeah, okay. What relationship can we pull out of that? Which one of them is constant? Nope. Nope. RC is the constant one. Yeah. So we can get a relationship between VC and I tot. So we know that VC is proportional to I tot. Okay, now we start to get something useful here. If I told you that can you see the chain that these have both got I tot in? So we actually have a relationship here together of VC is proportional to 1 over R tot. Okay. If I told you that the resistance of this decreased, what does that affect? Don't jump to through equations. I mean, what's the first thing immediately that affects? If the resistance of this decreases, what do I know? Is this in a relationship which has got some constant going on? It's not in a relationship that's got some constant going on, so I'm not going to be able to relate it to a voltage or a current. I can't tell because the voltage across this and the current through this will change. So that's not the relationship I'm going for. The R of this has gone down. What relationship can I use? R parallel, okay. What does R parallel equal? R parallel is equal to 1 over RB plus 1 over R LDR. Yeah. RB is constant, therefore there is a sort of positive correlation. It's not a proportional relationship. I'm not quite sure how to do it. I'd say, yeah, positively. I'm just going to draw one of these. And that's proportional, isn't it? Whatever. You understand what I'm saying? That if R LDR goes down, that goes down. If that goes up, that goes up. How do we know that? Because that's constant. So we've just got two variables in this relationship. Okay. So if this goes down, we know for sure our parallel goes down. Okay, what else do we know for sure if our parallel goes down? We can either tell something about a current, or a voltage, or a resistance. Which one can we say for sure we know about? So I've just had a suggestion that I tot is constant. It's not constant. V parallel is not a constant. It's going to depend on the resistance of this, and it's related to the current through this I tot. Similar to what we've tried to say something about V, we've tried to say something about current. What's the other option? We can say something about resistance. Okay, so if R parallel increases or decreases, what other physical quantity do we know about for sure? This is a constant. R tot we would know about because we know that R tot is equal to R parallel plus RC. We know RC is constant, so we know if that goes up or down, that's going to do the same. As soon as we've got that, boom, we have all our relationships. So R LBR goes down, causes R parallel to go down, causes R tot to go down, causes I tot to go up. We can say that because V tot's constant. Causes VC to go up. We can say that because RC is constant. If VC goes up, what can we say? Another relationship I've not written on here. Yeah, because V tot is constant. So it's when you've got these relationships where equations where there's only one, where there's only two variables, you can then relate those two, and this goes up, that goes down, or this goes up, this goes up, type situation. And you have to chain your way through those in order to find the relationship. So now we've been able to say V parallel has, where did we get to? We said this thing had gone up, therefore this thing has gone down. So we know the voltage across this is decreased, which is the same as the voltage across this. So what's happened to the current through this? The voltage across this has gone down, and we know V parallel equals IB RB. That's constant, therefore these things are proportional. If that's gone down, what's happened to IB? It's gone down. Okay, so if we decrease the voltage here, the resistance here, then our current through here decreases. Yeah? Massive chain of things. Now there are other shorter chains, but this was a nice one because it went through everything. And some of the key ideas are identify which of your physical quantities are actually constant, and then build your relationships around those. Huh?